morning children. Today let's start with chapter 10 circles. Let's review on the definitions and the terms used in this lesson. First, the definition of a circle. The set of all points in a plane which are at a constant distance from a fixed point will form a circle. That is, the set of all points in a plane which are at a constant distance from a fixed point will represent a circle. The fixed point is the center of the circle and the constant distance will represent the radius of the circle. So how do you define radius? Radius is a line segment joining center to any point on a circle. There are infinite radii for a particular circle. What do you mean by the diameter of a circle? When you take 2 points A and B on the circle, and if you join AB through the center, the line segment AB will represent the diameter. That means the diameter of a circle is a line segment. It's a line segment passing through the center, and whose endpoints lie on the circle. It is also a line segment, but it passes through the center of the circle as well as its endpoints are on the circle. And the relation between diameter and radius, as you can see in the picture, diameter is equal to 2 times radius. The length of the diameter will be 2 times radius. The next relevant definition is on a chord of a circle. What do you mean by the chord of a circle is, if you have any 2 points on the circle and if you join those 2 points by a line segment, it need not be compulsorily through the center of the circle. Such a line segment will represent a chord of a circle. So what do you mean by the chord of a circle is, it's a line segment whose endpoints lie on a circle. So from the figure you can see AB represents a chord. The question is, are all diameters chords? Are all diameters chords? Chord is a line segment which should have 2 endpoints on the circle. Definitely diameter is also a line segment with its endpoints on the circle, which shows that all diameters are chords. Yes. But are all chords diameters? Are all chords diameters? The answer is a no, because as in the picture you can see AB represents a chord, but it need not be a diameter always. In the figure here, if the rectangular region represents a plane and a circle is drawn inside this plane, the circle divides the plane into 3 parts. That is, the exterior of the circle, it's an exterior of the circle, the circle itself as well as interior of the circle. That is, a circle divides a plane into three parts: exterior of the circle, circle itself and the interior of the circle, and the circle together with the interior will represent a circular region. We used to say the circle along with the interior will represent a circular region. The next concept is the circumference of a circle. What do you mean by the circumference of a circle? Is the length of the circle or the full distance around the circle will represent the circumference. That is, the distance around or the length around a circle is called its circumference. The distance around the circle is called its circumference. And now, if you consider a part of this circumference and restrict that part to 2 points A and B, a part of a circle will represent an arc of a circle. Any part of a circle is called an arc, and the symbolic in the figure, arc AB represents a minor arc. If the length of the arc is small, it is a minor arc, and in this direction, if you consider this arc, it is a major arc. So, if the length of the arc is more, it is a major arc, and here it is a minor arc. So, any part of a circle is considered as an arc. The next definitions are: what is the sector of a circle and what is the segment of a circle. Imagine a circular cardboard piece. Imagine a circular cardboard piece, and if you join two radii and the region enclosed by these two radii and the corresponding arc AB will represent a sector of a circle. That means, take a circular cardboard piece, make two radii, and if you cut out the piece AOB, then that particular shape will represent a sector of a circle or area enclosed by two radii and a corresponding arc will form a sector. In the figure, the sector is a minor sector. The sector formed by a minor arc, sector formed by a minor arc is a minor sector, and if it is formed by a major arc, it is called a major sector. And the sector formed by a major arc is a major sector. The measure of this arc AB, angle AOB is the angle subtended by the arc at the center also. So, the sector angle, we call it as angle AOB. What is the definition for a segment of a circle is? You imagine a circular cardboard piece. If you draw a chord AB, the area enclosed by the chord and corresponding arc is called a segment of a circle. In the figure, this segment is a minor segment, and if a segment includes the center of the circle, it's called as a major segment. It's a major segment. This definition is area enclosed by a chord and corresponding arc is called as a segment. If the segment contains the center, it will be a major segment. What do you mean by the measure of an arc? The angle at the center of a circle is always 360 degree. In the figure, arc AB is a minor arc, and if you join the endpoints A and B with the center, you will be getting angle AOB, which is known as the central angle. Or the measure of arc AB will be always the central angle AOB. Once you say measure of arc AB, it says that it is the minor arc AB. So what will be the measure of major arc AB? We call it as reflex angle AOB. This angle is called reflex angle AOB, and it is calculated as 360 degree minus measure of the minor arc AB. As the angle at the center of a circle is 360 degree, reflex angle AOB is always 360 degree minus measure of minor arc AB. That is the basic knowledge on the measure of an arc. And in this lesson, there are certain chord properties, and the first property on chord is equal chords subtend equal angles at the center of a circle. The first property is equal chords subtend equal angles at the center of a circle. What do you mean by this property? If AB and CD represents two equal chords in the circle with center O, equal chords subtend. The meaning is they make equal angles at the center. Chord AB subtends AOB at the center, and chord CD subtends COD at the center. As per the property, if AB and CD are equal, then angle AOB is equal to angle COD. Equal chords subtend equal angles at the center of the circle. In the figure, if AB and CD are of equal length, then angle AOB and angle COD are equal. How can we prove this property? It is given that in the circle, AB is equal to CD, and what is to prove is angle AOB is equal to angle COD. Just consider the two triangles AOB and COD. Proof: in triangles AOB and COD, AB equal to CD, it is already given. Then is equal to OD or OA is equal to OC. OA is equal to OD. Then OB is equal to OC. The reason is radius of same circle. Therefore, there are three equal measures on one triangle which is to the corresponding parts of the other triangle, which shows that triangle AOB is congruent to triangle COD by SS congruence. Therefore, the corresponding parts are angle AOB and angle COD. They will be equal as corresponding parts of congruent triangles. So, what is the first property? It is equal chords subtend equal angles at the center of the circle. What is the converse of this property? Equal chords subtend equal angles at the center of a circle. What is the converse statement? The converse statement is chords which subtend equal angles at the center are equal. That means if you have a circle in such a way that AB and CD represents two chords, and if angle AOB is equal to angle COD, then immediately AB and CD are also equal. So what will be the converse statement? Chords which subtend equal angles at the center are equal. So that is property 1 and its converse. What is the second property? The second property says that in a circle, if you have a chord AB, a perpendicular drawn from the center to any chord, it will bisect the chord. That is, in a circle with center O, if AB represents a chord and if OM perpendicular to AB, then AM is equal to MB. In the figure, AB is a chord of circle with center O. OM perpendicular to AB, therefore AM is equal to MB. That is, the property states that in a circle, a perpendicular from the center bisects a chord, or a perpendicular from the center to any chord bisects it. So the second property is in a circle, a perpendicular from the center to any chord bisects it. What will be the converse statement? The converse statement will be in a circle, a line joining center to the midpoint of a chord is always perpendicular. That means you will have a circle with center O, you will have a chord AB. You can find the midpoint of the chord AB. The line segment joining the center to the midpoint of this chord will always be perpendicular. So the converse statement, a line joining center to the midpoint of a chord is perpendicular. So these are the chord properties 1 and 2. Let's proceed with exercise 10.1 and 10.2. Exercise 10.1, question number 1, fill in the blanks. The center of a circle lies in the interior or exterior of the circle. The answer is in the interior of the circle. First answer is interior of the circle. A point whose distance from the center of a circle is greater than its radius lies in the interior or exterior of a circle. That point will definitely lies in the exterior part of the circular region. Number 3, the longest chord of a circle is the diameter of a circle. The longest chord is always the diameter of the circle. An arc is a dash when its ends are the ends of a diameter. That means you will have a diameter. The endpoints A and B will represent an arc. That arc will represent a semicircle. It will be half of a circle or it is a semicircle. Segment of a circle is region enclosed between an arc and the corresponding, between a chord and the corresponding arc. A circle divides a plane on which it lies into 3 parts. Which are the 3 parts? The exterior, circle itself, and the interior. So the answer is 3 parts. Now, question number 2 for true or false. Line segment joining center to any point on a circle is the radius of the circle. It is a true statement. Number 2. A circle has only finite number of equal chords. No, it can have infinite number of equal chords. So the given statement is a false statement. If a circle is divided into 3 equal arcs, then each one is a major arc. It cannot be. The answer is false. A chord of a circle which is twice as long as its radius is the diameter of the circle. It is a true statement. Sector is the region between the chord and corresponding arc. Sector is between the radii and the corresponding arc. So the given statement is false. A circle is a plane figure. It's a true statement. Exercise 10.2, question number 1. Recall that 2 circles are congruent if they have same radii. Prove that equal chords of congruent circles subtend equal angle at the centers. That means we need to verify the property with the circles having the same radii. Prove that equal chords of congruent circles. That means you are given 2 circles whose radii is the same, whose radii remains the same. Given 2 circles with same radii. In the first circle given chord AB and in the second circle given chord CD, but they are equal chords, and AB and CD are 2 chords such that AB and CD are equal. And what is to prove is they subtend equal angles, which shows that angle AOB and angle COD are equal. So angle AOB is equal to angle CO dash. How to start with the proof? As we proved for the property, in triangles, the proof starts as in triangles OAB and O-CD, since the circles are congruent or their radii are equal, OA equal to O-C, OB is equal to O-D, and both radius AB equal to CD given. Therefore, triangle OAB is congruent to triangle O'CD by SSS, immediately angle AOB is equal to angle CO'D. That is, if two circles are congruent and if you have two equal chords in it, the angles subtended by the chords at the center are also equal. Question 2. Prove that if chords of congruent circles subtend equal angles at the center, then the chords are equal. Just the converse statement. So, in the figure here, given two circles with center O and O'. They are congruent circles, which shows that the radii are equal. And AB and CD are two chords such that the angles subtended by them are equal, which shows that angle AOB is equal to angle CO'D. And what is to prove is the chords are equal. The proof as the same, you have to prove the triangles are congruent. In triangles OAB and O'CD, OA is equal to O'C radius for radii of the congruent circles. OB is equal to O'D and angle AOB is equal to angle CO'D given. Therefore, triangle OAB congruent to triangle O'CD by SAS, AB equal to CD as CPCD, the corresponding parts of congruent triangles. Thus, the first property as well as the converse we are proving in case the circles are congruent circles.